PhD from University College of Swansea in Wales, UK, for the physical modeling, scaling, and numerical analysis of quenching large-scale force flow-cooled superconducting coils. He has experience in the design and testing of superconducting cables and magnets for fusion, net, and ether, as well as accelerator magnet design, manufacturing, and testing with CERN, LHC, and H-field magnets. He is author of computational methods used for magnet design and analysis, and from 1995 to 2004, he created the field description for the LHC, FIDEL, now an embedded system for the LHC control of field quality and corrections. He presently contributes to the magnet research and development at CERN, especially for muon colliders and the development of accelerators for particle therapy. Luca, if you can please share your slides.
I will. Thank you very much. George, thank you very much all. And thank you very much for the opportunity to talk to you about this idea, which is progressing, as somebody said just before. So the idea is of a toroidal gantry for particle therapy. I'm going to present it, and it's the work of many. So I listed some of the names of people that have contributed significantly. And there's many others, of course. And you will see a list of references at the end of produced reports, presentation, and papers if you're more interested. Don't hesitate to contact us, any of us. And I also need to acknowledge gratefully the support of the knowledge transfer unit here at CERN, and in particular the budget for medical applications financed a lot of development, students' work, as well as material for the testing that you will see. So George, if it's okay, I'll go ahead with the presentation now, right? I guess yes. Right. Okay. So the presentation is a short introduction to what we need to do for therapy of cancer using radiation. Some of you may know even more than I do, but just be patient, because then that's a good introduction of what is GaToroid, what the variants of GaToroids are. And there's several instances that we try to design to see what the opportunities are. And then eventually we'll talk about the magnet design and development we've done so far, opening a parenthesis about the superconductors that we wish to use in the future, and which brand and why do we want them. And then eventually a couple of slides of summary and perspectives. So as to radiation therapy, it's a long history. I mean, it's coming up big in the hypes in the past 20 years, but it dates back to the late 1800s. So possibly 1896, when a treatment using high dose of ionizing radiation was first proposed to kill actually tuberculosis, virus, bacteria, but recently cancerous cells by damaging their DNA. And then as a result, shrink the tumor volume. And now what you can see here is a first instance of an early treatment of tuberculosis. So this is the X-ray tubes at that time, dating back 1910. So as far as that, and of course, if you contrast that to a present machine, a modern linear accelerator, that doesn't look quite the same. They don't quite do the same, but it's a pioneering work that took us there. You can use different particles, different radiations to do therapy. It is used actually in the treatment of about half of the cancer cases worldwide. So photons are used in most of the treatment. The dose that they deposit, which is plotted in this plot here, so that's the dose on the vertical axis as a function of the tissue depth, so inside the body. So the dose is for photons is actually peaking when the photon hits the tissue, more or less, and then decays more or less exponentially. Other particles deposit their dose differently, like hadrons. I'll come back in a second. But hadrons, they deposit an initial dose, which is not too much, and then eventually a very high dose when they stop, and then there's no dose afterwards. Electrons, different particles again, they're very different in that they deposit dose when they enter the tissue, but then at a certain moment they actually die out at low energy, or they can penetrate tissues and they deposit relatively higher dose inside the tissue than they do at the beginning, and then eventually they die out, they go out. So as you see, different particles, different radiation photons can be used to deposit different type of doses in different locations. So this is interesting, and particularly hadrons are interesting because, as I mentioned, they have a feature which we call the Bragg peak, actually, which is called the Bragg peak. It's a pronounced peak in the curve, which plots the energy loss. So that's the same as we had before. So dose versus depth. As radiation travels through the matter. Actually, that's corresponding immediately before the particles come to rest. And it's named after William Henry Bragg, who discovered it in 1983. And then it was one of the features that was put forward by Bob Wilson in 1946, when in a paper in radiology, he proposed to use fast protons for radiation therapy. Okay, so you see ideas dating back. In the meantime, people have realized that you can use these features of the Bragg peak, which depends on energy, by the way. So by having different peaks, you can enter different depth in the tissue, and the depth you enter, so the peak location, depends on the energy, and it's called the range, and it's this plot for protons and carbon ions, which are two particles that are used for therapy nowadays. So protons, they tend to have a smaller range for a certain energy. Carbon ions, they tend to have a higher range for a given energy. So essentially, this Bragg peak moves about depending on the hadron type that you are using. Now, an interesting feature of that peak is that you can use different energies in different beams and then compose the beam effects to get an effect like this. It's a composition of Bragg peaks to have not just one dose location, but changing energy to have multiple dose locations that superpose. Now, that is used in radiation therapy, typically to have what is called the spread out Bragg peak. So the machines that are delivering particle, like let's say protons, so they can deliver different energies and different intensities. And then by sending different fractions of radiation into the tissue that needs to be treated, what you can get is a dose total that you can see from the top red curve here that I'm pointing to. So essentially, you superpose the Bragg peak until you get a useful dose, which is relatively high at the tissue location where the tumor needs to be treated. And for hadrons, you will have lower dose at the entrance because of the Bragg peak, and lower dose at the exit because as soon as the particle stops, there's nothing else happening. Now, this is contrasted, by the way, to what you would get with photons. That's a blue curve, where you get the dose that is relatively high at the entrance, and then it goes on till the exit. So in essence, the area shaded in blue is the leading edge of hadrons versus photons. So the additional dose that you will get in tissues that you would need to spare is the blue area, and that's why there's interest in hadrons. Now, this is depicted here. So I've taken graphics from Proton. So if you have X-rays, the X-rays, they actually go through, they deposit those, but they also irradiate other tissues. The protons, you can calibrate them so they deposit those all the way to the tumor to be treated, but not beyond that. So that's the first interesting feature. Now, how can you combine these various effects? Actually, there's an idea of 1968. It's called the gamma knife. Lars Lexell, who invented a device that was equipped with radioactive cobalt sources placed at angular spaces in a source device, and then a helmet which would have collimators letting the radiation enter or not. So you would actually focus the radiation from different sources into one location. So several precisely collimated beams can be superposed, and it gets an additional effect, sparing tissues around, but a high dose where you want to collimate. Now, this is done nowadays by different means. So you can do that by sending beams from different directions. And this is shown here. These techniques, they require the ability to deliver beams from multiple directions. But the additional benefit is that, as you see from the pictures here down at the bottom, that depict the amount of dose into the tissue with a certain tumor area to be treated, the various techniques, they realize very high dose, the red areas here, and the relatively low dose, the blue area here, depending on whether you move the beam or intensity modulate or volume modulate. Okay, so a question actually, because to generate these beams, you need an accelerator. So as usual, the accelerator is a relatively expensive, big, bulky component. It's not easy to change the direction from which the beam is coming from. A question that arises is whether can we move the patient? And in fact, there are machines that can do that. But the issue there is that if you go from a supine to a seated position, as an example, the motion of the organs inside the body is significant. Like in this case, going from supine to seated, the liver moves by about 20 millimeters, 2 centimeters. So that says that if you want to treat precisely, we're talking about millimeter accuracy that is typically required. There's only small motions can be tolerated because of the accuracy that is requested for the organ positioning. So most of the time, the preferred situation is with the patient which is supine, so on a bed. Now there's other movements too, and I've taken this picture from a study from Enrico Felcini when he was doing his master thesis. So this is, as you can recognize, breathing. And if you have a certain area that needs to be treated, which is the area marked in red here, you see that during breathing movements, that area moves by a few centimeters. And there's something in addition, the fact that if you treat a cancer, through the various fractions, the cancer actually changes. And an area which looks like the area here, okay, the red marking is not quite precise, but you can see, that there was the red marking, becomes 3 weeks into treatment, a quite bit different. So you need to re-image and make sure that you actually treat that area. So the dose needs to be delivered precisely and possibly rapidly. Moving organs and changing the morphologies are a challenge. Okay, so as we are through the introduction, obviously there's the usual debate between engineers and it's usually physicists, but in this case it would be physicians. Now the ideal subject of radiotherapy for an engineer is a homogeneous, perfectly rigid and immobile patient. That is not very interesting subject for a practicing physician. So we have a challenge here. So what I want to say is that anatomy, the motion, changes are major challenges for any radiotherapy. And in vivo and online imaging and range measurement would be the holy grail today of radiotherapy. This is not quite the topic of this talk, but maybe related to, because as you will realize, with the GaToroid, which is a steady equipment, you may be able to integrate also imaging devices that are very useful. Right, so where we stand is that we understand the interest of different particles. We understand that hadrons have different features than photons. Actually, some of the features are very interesting. Hadrons you produce with accelerators, but then you need to direct the beam from different directions. And so how do you do that? And nowadays you do that with gantries. So gantries are essentially transfer lines. Now, let's take this one in the middle here. So it's a transfer line that receives beam from the accelerator and then bends the beam and puts it at, say, 90 degrees with respect to the patient who's sitting right in the middle of the gantry here. The gantry structure can rotate by 360 degrees, typically, and that allows the beam to come from different directions, so you can scan around. So these objects here for protons, you see here dimensions, tonnage, so that we are talking about tens to hundreds of tons. A very different device is the one from Mevion, who puts the accelerator on the gantry itself. So you don't need a transfer line to go around. It's the accelerator who goes around. With a small difficulty that you also generate neutrons by doing that, but that's a different story that they dealt with. Especially for carbon ions, what you see here, because of the rigidity of the beam, which is about 3 times as large, the sizes of the proton gantries, they triple. So that means that the typical size becomes 2 to 3 times as much. The typical mass becomes 3 times as much. So this is the first therapy ion gantry that was used by Heidelberg Therapy Center followed by superconducting versions by Toshiba, and then a recent realization a few years ago where the size and mass has been reduced to about 240 tons. So these are still massive objects. Can we do better than that? And that's the origin of this idea of what we call the GaToroid. And in fact, the idea of GaToroid is to have the accelerator that delivers beam that goes through what we call the vector magnet. So that's an XY kicker, which can switch fast, sending beam in different direction. So these beams in different direction, they get bent by the toroidal magnet. So this is the lines of the toroidal field. And this field is steady state. And by being bent, they're bent on the location of the patient. And that would allow a fast direction switching because of the steady state toroidal field. Okay, so that's principle number one. Principle number two is that the accelerator beam that is delivered into the vector magnet not only gets sent to different direction in X and Y, but also in different angles. And so beams of different energy are directed to different angles so that there's a large acceptance superconducting magnet actually at the end with this toroidal periodicity, so generating the toroidal field, operating in steady state that sends the beam to the patient location. And fast energy switching is possible because of the steady state field and large acceptance. Okay, so these are the two basic ideas that led us to the development of the concepts. Now, it's easy to say, how do you do that? First of all, what is a toroidal field? Well, a toroidal field is the field that is generated typically on a torus, like here an iron torus. If you send a current around the torus on a toroidal winding. So the field, this is kind of just a nice sketch of the lines of field as seen by iron barrels. And so the field typically has a peak in the inside of the torus, and then it goes down like 1 over the radius. Okay, so it's not necessarily a constant field. Now, what is the effect on a torus field on a beam? And let's take to start a parallel monochromatic beam. So there's beam with parallel direction, same energy for all the particles. What happened to that? Well, as we said, this is the torus. The field is actually going like 1 over r. So it's inversely proportional to the radius. That means that the kick that the beam receives is actually inversely proportional to the radial position of the beam. So that means that in that case, a pure toroidal field is actually opening up a monochromatic one-direction beam. If you have a divergent monochromatic beam, so from a single point, and you open up the various directions, you will still have a divergent direction at the end. Now, if we think about a thick toroidal field rather than a thin toroidal field, what happens is that because of the extent of the magnet, which is the blue outline here, if we take the effect onto a parallel beam, we see that the parallel beam that is outside sees less field, yes, but on a longer length. And the field that comes from the inside radius sees a higher field, but on a shorter length. And in the end, you can balance things using geometry such that the effect is focusing. Okay, so going from thin lens to thick lens, we can profit from the extension of the field and get a focusing effect. The same happens from a divergent monochromatic beam. Okay, so that's just an explanation of that. So a toroidal field of finite length has a net in-plane focusing effect on a monochromatic beam due to the fact that the integral of the field depends on the radius. Now, if you have a parallel and divergent beams of different momenta, what happens then? So let's take, first of all, parallel beams of different momenta. Well, the different momenta, they will be focused at different locations along the axis, even from a finite sized toroidal field. Now, we can play, though, with the angle, and that's the function of that vector magnet that you just saw, by sending higher energy beams further out in radius so that they integrate the field on a longer length and smaller energy beams inside so that they integrate the field on a shorter length. So the net effect, if you balance the two, is that you can focus again different energy beams on the same point. So using thick lenses, we can play with the angle and get multiple energies focused on the same point. Now, to finish about the focusing effects of a toroidal field, so a toroidal field has field lines that go around like circle. So if you look into the field components, that's just b theta, and then you project that in a by and bx. And if you look at the by at a location at x equals 0, you see that there's nearly a gradient, right? So at small angles, that b theta projects like sinus theta, which means like x. So that means that out of planes beams, so beams that come out of these planes, on the vertical axis y, they get actually focused like a quadrupole. So that's interesting because a toroidal field focuses essentially in two planes. It's like a solenoid. Now, composing the whole idea of a thick lens, different angles, playing with the profiles, we've done that by computing the ideal coil profiles that, coupled with the ideal angle, would result in perfect focusing of different energy beams. Okay, so what you see here at the 0 minus x vector location is the vector magnet that sends the beam, and then this is the main band magnet that actually focuses the beam into a single location. Okay, all the beams are 90 degrees. So, and that would be an ideal coil profile. Now, all these calculations have been done with a constant field. As you've seen, we don't have a constant field, but this coil profile would delimit the field area, which is focusing the beam. Now, I mentioned the field is not actually constant, but there's a way to make that constant. And instead of building a coil, which just goes around the torus and produces the field that goes like 1/r, you can actually spread out coil windings so that you put less current inside, more current outside, and you even out the field. So actually you play with the position of these coil grades, as we call them, you can actually introduce an index to the field. It can be flat, it can be positive, it can be negative. And this is the demonstration of that field profile you've just seen. It's kind of a simplified coil. To give you an example, along that length, which is the radius, outer direction, you look at the field versus the length. So this is the length on the radius. We see the 1/r dependence inside the coil. So we are entering the coil, inside the coil, outside of the coil. But we can play with the grades. And what you see is that that 1/r dependence is actually flattened out. It's not perfect. It's not needed, because then you can play with the angles to get that field to focus as you like. Okay, so now let's see what it looks like. If you put all these coils together, you generate a toroidal field. The toroidal field is actually the one that bends the beam, and the patient is located inside the toroidal magnet. Now, the vector magnet action is to send the beam at a certain angle, which is calibrated with a certain energy, so that the effect is to focus the beam onto a certain location. And then the vector beam can move and send a different energy beam to the same location, or move and send an energy beam from a different angle. So that in principle, you can irradiate with different energies and different angles just by acting on the vector. Okay, so this is very important. Essentially, as you see here, you play with the angle kick. The toroidal field is constant. You don't need to change it. And thanks to the acceptance, you can actually do stereotaxis. So you map the tumor with different energies so that you spread out the Bragg peak, and different angles so that you come from different directions. So that's the principle of the direction of the GaToroid. Now, that's the idea. What you just saw is the realization for protons. We've looked into variants with different outcome. So the proton version would look like, in the minimal version, like something like this. So you've seen the previous images. That's a standard doctor to give you the size. So we've designed it for 16 angles. It has a stored energy, which is relatively reasonable. So we're talking about 30 megajoules, mass of about 10 tons, 12 tons, so it's not much. The only difficulty in that, doctors today don't like to insert the patient in a machine like an MRI. They would like to have full access and actually the possibility to fully rotate the patient. And that's what gave rise then to the next iteration, which is the ion version of that, carbon ions, for which you need higher rigidity. It was built for a larger bore, just because of that request to be able to rotate the patient inside the bore. This becomes a machine that has a stored energy of a gigajoule and above, and a mass of 300 tons. And so we realized that trying to realize what the machines do today with a new concept is not a good idea. So we tried to see whether a smaller version of that could be realized. So only with 8 directions, yeah, I should say the previous direction of delivery of beams were 20, because that was the request. Now, limiting that to 8 directions and still a relatively large bore, so more than 2 meters, you would come still to an object which is 130 tons. So it's quite large, it's quite expensive. So it's not necessarily the best realization of the machine. And that's why we started looking with interest at other features of radiation therapy that have been emerging in the past years. And one in particular is what is called the flash effect. So flash is a method of delivering doses within a very short time, so about 100 milliseconds, and relatively high, so it's called ultra high dose for dose delivery to bodies, but let's say above 40 grays per second. So flash has been shown to preserve normal tissue and still have the same effect for the same dose to the tumor tissue. So that means that you can deliver either the same dose with less adverse effects, or you can leave more dose, actually attacking radio-resistant tumors, still having the same effect on the normal tissue. So the fact that, by the way, electrons in particular can be delivered rapidly makes very high energy electrons an attractive candidate for flash therapy. And there are, in fact, a number of machines that are being looked at. One of them is being built as a collaboration between CERN and the Lausanne University Hospital. Another one is being probably built, I don't know the status, but it was an idea at Stanford University in the USA. And you see here images of the two technologies as they're being realized. Now, one thing to be said is that it's not clear where the flash effect comes from. It has been demonstrated and measured for electrons. It has not yet been demonstrated and validated for hadrons, so protons in particular. It is thought to be related to anoxy, so lack of oxygen during the short period for the cells to actually damage because of radiation. But as I said, it's not clear. So research is required to go further on that. And that's one of the elements that I will come to. So in the end, we looked at the GaToroid options for hadrons, protons, compact, ions. It becomes much bigger if you want to satisfy medical requirements. And ions minimal version is still quite big. Now, why would you look at GaToroid for a very high energy electron machine? Well, there's a few reasons. One is that the electron beam rigidity in the range of interest, which is 100 to 200 MeV, is approximately 1/3 of the proton beam rigidity in the range of interest for therapy, which is 70 to 250 MeV. So in that case, if you want to build the magnets, because of the lower rigidity, the GaToroid would have much reduced size, weight, cost with respect to any proton or ion version. And that makes a study on very high energy electrons very interesting if you have a possible demonstrator. Now, the second thing is that with a GaToroid, as you've seen from the demonstration of a typical therapy session, you don't need to change the magnet. So essentially, it has inherent flash capability with multi-directional treatment. So you can do 3D conformal mapping, multiple direction delivery to map the tumor, but in flash mode. And you cannot do that if you rotate a classical gantry. It's way too heavy to move in 100 milliseconds. In fact, even if it's not requested for a very high energy electrons, which are typically running on a single energy, it would be compatible even with flash at multiple energies. So today it's not a request, but it's a possibility. And in fact, this is why we try to design for very high energy electrons a typical transfer line So in this case, what you see is that there's a vector magnet here. You see in a moment that it's no longer a vector magnet. We call it a resonant kicker now. Then there's a toroidal septum that kicks the beam up, that goes then into quadrupoles, toroidal quadrupoles, and then eventually in a final band, a toroidal band, that sends the beam to the patient location. Okay, you get here the characteristics of the various magnets. What do they need to do? And a feature in electron therapy is also that you don't generate pencil beams. There is no point in scanning. Also because of the flash effect, there the idea is to try and generate a flat beam. So that means that a beam that enters maybe small here is manipulated by the quadrupoles so that at the exit of the final band, when it comes to the patient, is actually centimeters wide. So you see the scale here, we're talking about 10 centimeters in total. Okay. If you are interested in the optics, I put in the slides references to optic studies. So this is the support we're getting for the magnet design. I guess at some point the slides can be made available. And now that's what a GaToroid for very high energy electron could look like. It becomes quite interesting in itself, as you see. So it's a 7 directions machine for 200 MeV. It has a length of about 4 meters, an outer diameter of about 4 meters. The patient will be located in the middle of the final band, and that's where the beam goes. So that's the red line here for one direction. There's a final band, which is a toroidal dipole, and I mentioned rigidity, which is smaller. In this case, the Bohr field is only 1.5 Tesla, and you need a few hundred kiloamp turns, so it's not very large current for an aperture of the order of 80 by 200 millimeter. Interesting beasts are the toroidal quadrupoles, so I'll comment on that. So there's quadrupoles that generate a gradient which is modest on an aperture of 58, 60 millimeters, and then a toroidal septum here. So this is the amplifier of the angle kick. Total 17 tons, 3.7 tons weight, and 21 tons for the system. So these toroidal dipoles, so there's an iron yoke, coil pairs that are generating the field. You see here the field map across the aperture. So if I cut in this plane, and the field map in the aperture as you go along the beam with S. So the longitudinal field that has been generated is quite flat with entrance and exit effects. And with just a first attempt, we get 1% homogeneity over the useful aperture, which is 5 centimeters. So that's quite an interesting magnet. The coils, they don't need to be resistive. They can be superconducting, by the way, so to reduce energy consumption. To the toroidal quadrupoles, so there's poles here that are powered by single coils. And then as you realize, so the flux return of each quadrupole, instead of closing on the magnet itself, closes to the next one, and the next one, and the next one. You get a nice quadrupoles. The requirements was about 16 Tesla per meters. So this is the field profile in the two planes, the red and the green. They superpose nicely. The effects here that you see outside, they're outside of the aperture, and that's because of this small non-symmetry between the two returns yoke outside and inside. Longitudinal field profile is also quite flat, entrance, end effects, and then a nice quadrupole in between. Now to the kicker, one of the difficulties we realized with the first realization of the GaToroid was that the kick had to be very precise. So you needed to be precise to milliradian or sub-milliradian onto the angle. So that's not easy, especially if you need to ramp up quickly, send the beam in a certain direction, and every error amplifies. So we came up with a different idea, realizing that the timing of the beam delivery can be relatively precise, so it can be microsecond precise. And the idea we came up with was to use a two-plane corrector magnet, so like this one that has been used and built for the ELENA, so low energy storage ring at CERN, where there's cosinus theta resistive windings, one inside the other, that generate a vertical and horizontal field. So it's in cross-section, it will look like this. So these two windings, they can generate fields of the order of a couple of tenths of Tesla, say, a couple of 100 millitesla. And you can make them oscillate. So you can put them in a resonant mode, so the vertical and the horizontal one. Then you can trim the phase and amplitude, and essentially what you can get is a rotating field. So if I look at the field Bx and By, I can generate a harmonic field in Bx and By, and depending on the time at which the beam is sent, you will get, as an example, at 25 milliseconds, exactly an X kick, at 100 milliseconds, exactly a Y kick, and at 80 milliseconds, a kick somewhere else. Now, phase and amplitude can be very precisely controlled, and timing can be very precisely controlled. And by doing this, we believe that you can get rid of the accuracy requirements on the actual vector magnet that we had at the beginning. Now, a few comments about the magnet design and development. So you've seen the coil of the proton GaToroid. We actually realized one. We realized a single coil of the proton gantry scaled by a factor 1/3 to test the magnet performance, quench protection, field profile, and the manufacturing. We used two different cables. One was based on a stack of HTS, one was based on a niobium titanium small cable. All of them were actually encased in copper, either profiles, like the case of niobium tie, or copper tapes, just to add the copper for protection reasons. So what you see here is a cross-section of the cable we used. So this is the exploded version of the various of the magnet. It's actually the same geometry for both HTS and niobium tie. You see here the parts. It looks quite neat, and it doesn't look too complicated in the end. So the demonstrator itself was built over the past 3 years, more or less. HTS first, niobium titanium next. And in fact, the results for the HTS one, that was the first build, was a bit disappointing, I must say, if not to say very disappointing, in the sense that we produced the magnet after validating the stack technology. The stacks were impregnated, and then we realized only after having made the magnet that there was an issue with the tape. So the tape had such a small amount of copper and steel and silver as coating, as capping, that just by winding it, you would actually rip it up and expose the superconductor to whatever the agent was outside during impregnation in particular. So we believe that chemical incompatibility actually has depleted oxygen in the superconductor, which realized that the magnet did not perform. It was barely superconducting. The results of the niobium titanium test were much more comforting, and in that case, the magnet was powered, and so the dots that you see here are the values of the field versus current that were reached during powering at 4.2 K, so that's the dot that is on the red curve, and at 1.9 K, which is the dot on the blue curve. And actually, the quench was corresponding to the critical current of the cable, evaluated from cable measurements. Now, the Bohr field, so that's what we call the Bohr load line, was obviously lower. So peak field, we reached about 3 Tesla, which is not much, still nonetheless, it's nice to get to the AC quite straight. And that allowed to measure very precisely the field and measure quite precisely quench propagation. We also did some ramp rate tests. We were a bit surprised because in the end, we went up to a field rates of 0.4 Tesla per second with only less than 10% degradation of quench current. So meaning that the temperature margin, let's say the heat margin was actually relatively large. So adiabatically, the cable could withstand very nicely the ramps. We measured the field, and in particular at locations, so I need to come back a second. So at various locations inside the coils, you can barely see them here. Let me see. Okay, so at various locations, which are these dots here in the coil, that are the locations where the field, sorry about that. So that's where the beam goes through. So to validate the fact that the field that is computed or designed for is actually the field that would be seen by a beam. And as you see here, there's been very good agreement between the simulation and the measurements. So we're talking about percent errors, and some of that percent error could be explained by positioning of the whole plates and the coils that were measuring the fields and their accuracy. We also measure quench propagation, and that's an interesting additional result in a coil like that. I need to go back again to show you a bit the coil. As you can appreciate here, several conductors touch each other. Each of these grades is multiple conductors wound. So there's a few windings here, few windings, and then many windings on the outside block. Now the peak field was at the layer grade, at the layer transition, so here in the center. So quenches typically would start at IC here and then propagate along the conductor, but also across the conductor. And in fact, modeling has shown that if you model the coupling between the conductor inside the grade, then you will get a relatively good match of the red curves and the black curves, which is simulation and measurements, over a range of data. But if you forget the coupling of the conductors, so there's thermal resistances between the adjacent conductors in a grade, what you get is the dotted black line down here, which has nothing to do with the real quench. So that has shown as well that that can be mastered and properly simulated so that you can guarantee protection. Now let me open a small parenthesis. I think I still have a couple of minutes about superconductors. So which superconductors first? So you've seen data taken with niobium titanium, not much luck with the HTS because of reasons we believe. But just to put you in perspective, superconductors are generally categorized in low temperature, high temperature superconductors. You see here the data, low temperature superconductors, they're superconducting up to 30, okay, MgB2, magnesium diboride is an exception, goes up to 40 K. Fields of the order of 15, 20, 30 Tesla. I mean, the values of MgB2, which are so high, is actually for thin layers, so it's something which is not a cable. And then you see high temperature superconductors, they're superconducting up to 100 K, so above liquid nitrogen, 77 K. But a feature that is mostly interesting for us magnet makers is that the critical fields, they're excessively high. We're talking about 100 Tesla and above. So HTS are not only superconducting at high temperature, but they're also very interesting because they have superconductivity properties at high field, which is important for high magnetic field applications. And in fact, one of the basic properties that we look at, not just temperature and field, is what we call the critical current density. And typically that is given by the current density that brings the flux lines to move inside the superconductor. And that's essentially a force that does that. And so that current density is defined when the force is broken. So there's a pinning force inside the material. J current density times the field is the force density. And if you exceed that pinning force, you're at critical condition. So you can define actually a critical current density, which is the pinning force divided by the field. And that's nothing else but this surface. So we call this the critical surface. So typical values for niobium titanium are given here. So if you are at 4.2 Kelvin, that's the horizontal axis on the base, and 5 Tesla, that's the horizontal axis on the base here, so that's the red line. The intersection has a critical current density of about 3,000 amperes per square millimeters. Now there's various materials, as you've seen before, the critical current densities are different. You see niobium titanium. So if you go to 5 Tesla and 4.2 K, your engineering current density, which is overall, not just a superconductor, of about 1,500 to 2,000 amperes per square millimeter. Niobium 13, which many of you know very well, is essentially twice as good on all the axes. Twice the critical temperature, twice the critical field, twice the critical current. And that's why it's used for high field. And then there's HTS, so these materials here. And what you see is that the 4.2 K, they're actually spectacular. They go to very high field. That's the main interest. Not only because even at high temperature, they're quite good. Okay, so you see here rare earth barium copper oxide, YBCO. It's actually very good even at 20 K. Now, the other feature that I want to make you look at is the fact that you may have heard HTS are complex, they're difficult, they're expensive. Well, they used to be, because if you start comparing the cost of HTS to the cost of niobium-13, and this has been normalized by the current carrying capability and then by meter length. What you see is that the cost of HTS is actually coming down very fast to meet the cost of LTS. So for all this reasoning, so the superconducting coil design, which has been demonstrated thanks to the niobium titanium test, can meet performance, field quality, quench protection. Next step is most likely a superferric demonstrator for very high energy electrons, 200 MeV, research in hadron therapy, 90 MeV, 250 MeV, which probably match the same rigidity, and surely REPCO is the material of reference. So that HTS operating at 30 to 50K will significantly reduce power consumption compared to LTS, a factor of 5 to 10, and will make cryogenic engineering much easier. And by the way, in the end, be actually cheaper. So in summary, and a slide of perspective, so at the beginning, the idea that touch of insanity, but actually, I believe it could result in a real quantum step towards a compact gantry, something that looks more like an MRI than an accelerator, and possibly ease clinical penetration of hadron therapy. So if you make it smaller, it can be a single room facility. So as for an MRI magnet, maybe it's too far, but reducing size is always useful. Low consumption, steady operation, fast switching of energy, you've seen the benefits. I mean, flash, stereotaxis, so that's only possible if you have a steady state magnet. So that could open up new treatment possibilities. One of the difficulties to the penetration is the fact that it's difficult to convince physicians that they can do things differently, and rightly so. I mean, you want them to do the right thing, not to experiment. But still, that kind of blocks evolution beyond what they can do today. So this could open the possibility on that. And then integrate new diagnostic and imaging devices. I didn't talk about that, but we had a study showing that you can put actually in vivo measurement of range and dose. So in perspective, there seems to be, in fact, an interesting design point to explore a magnetic configuration capable to deliver very high energy electrons, low energy protons on a flash time scale. Now, the very high energy electrons would be for therapy. So using resistive magnets, essentially, we would have essentially an already qualified device. Low energy protons would be for research, mostly to do organs, tissues, and small animals, to figure out whether flash works, how it works, and what the advantages are. So the research avenues is optimize the magnetic of this novel configuration. We have a few ideas that you've seen. Toroidal quadruples is something like a funny thing. The resonant kicker is another funny thing. Amplitude, phase, and timing needs to be demonstrated. And then we need to advance with the beam physics design, 200 MeV very high energy electron, as well as 90 up to 150 MeV for proton beams. And then introduce engineering concepts, in particular, evaluate the HTS superferric options. And last not least, it's important now to move to a full-size demonstration device. So meaning that a device that sees beam and actually shows that you can do not therapy, but research as a start. So a last slide, it's always interesting to go back in history. So where did that idea come from? So in fact, a few years ago, I'm sure you're aware, so there's talks about a human mission to Mars. So a human mission to Mars implies sending the astronauts for a minimum of a year. We're talking about 6 months on one way, 6 months back. And that results in an integrated dose in the range of 1 sievert, maybe mainly from the galactic cosmic rays. So there's not much you can do about that. And some of the things you can do about that is to attempt a magnetic shielding. So you bend the beams of cosmic rays as they try to enter the inhabitable part of the vessel. So that has been studied by NASA, by ESA, and there's a project which is SR2S that actually designed a toroidal field to deflect incoming particles and thus reduce exposures. Now, I admit it was in a conversation over a beer that we thought, hopefully, that the magnet polarity is right. Because otherwise, instead of deflecting the beam away from the astronauts, we'd actually focus the beam onto the astronauts. And that was actually the beginning of that idea of saying, hey, maybe we can focus beams with a toroidal field. Now, luckily, in the meantime, NASA is developing hydrogenated boron nitride nanotubes, so it's a very advanced material, and that's a lightweight radiation shield. And so they probably do even without, but we start doing therapy with the GaToroid. All right, thank you for your attention, and I hope you're still there.
We're all still here, Luca. We're all still
Thanks.
here.
So any questions in the room? I'll take them with mic or on Zoom, please raise your hands. Well, let's start. Luca, I have a question. How much engagement you have right now from companies, from the industry? Do you think it could be more? Do you think you need first to build a working prototype to get more? What do you think on that?
Right. So for the moment, there's no industry building this. We have two avenues. One is, it's two grants, actually. One is a Dutch grant we are applying to get funding for a first prototype. They will most likely be designed by institutes and then built by industry. The industry still needs to be selected. The second avenue is a European call. So we are thinking about a European proposal next year. It's an EIC, so European Innovation Council. Again, that would be for a prototype, and again, it will most likely be an industry building the prototype. So far, the leading industries for therapy, they're not, when we talked about them, we talked to them, but they're not picking up the idea yet.
Sorry, please.
Yeah, hey, very nice, Luca. So why did I don't think the physicians are used to wanting to rotate the patient, but here, you know, the whole motivation for rotating the patients. I mean, to me, you've covered the territory and angle. So why do they still want that?
Why do they still want what, Soren? I don't know.
To rotate the patient, you said, or is it in a different plane that they want to rotate? How do they want to rotate the patient? So you mentioned, because you had a nice compact design there that would look like an NMR, right? Or MRI, like you said.
Right.
But,
so there's a thing which is called the therapy planning software, and there is counting on the fact that you have access with the beam, essentially from all the direction of the tumor that you need to irradiate. So the gantry can go around, and if you have a rotating gantry, you know, the nozzle is actually just an object which is hanging somewhere, and you have a free space all around. So essentially, you can move not only the direction in one plane, but by moving the patient, you can change the plane. And
I see.
it depends on again, you know, it depends on what is called the therapy planning. And the therapy planning is something that needs to be qualified for use. So if you want to develop a different therapy planning, you need to qualify that for use, which takes time and money. And that's part of the resistance, you know, the potential barrier that you need to go beyond to get the device qualified. And this is why, you know, the demonstrator will have to be for research. You know, I don't think you can get a therapy demonstrator.
Right. Okay, thanks.
Yes, I have a question. Luca,
Sure.
Can you hear me? Yeah.
Yeah.
So I have a question because I was not aware of this last development, the VHEE option. So I was wondering, I mean, from your talk, I have the feeling that you think that this is probably more promising right now as an application compared to the original GaToroid, or is only my impression? I mean, between the two options, let's say, which one do you think is right now the one where you are investing more time, or the one that you think is more promising between the two applications? Yeah.
Right. Okay. So I think from the future point of view, electrons are probably more interesting than protons, because on protons you don't have the demonstration of the flash effect yet, as far as I know. So I mean, that's a whole field of research by itself. On electrons you do, but today with electron machine you cannot do stereotaxis. So you come with one or maybe two directions, and you don't have the freedom to actually map the tumor as you would do with protons. So a GaToroid for electrons would give you stereotaxis at flash time scale. And I think it's very interesting because it only adds multiple directions. Everything else is already qualified.
Mm.
For protons, having said that, the interest we get today, one of the two avenues, the grant from Holland, is actually on proton research. There's a particle therapy research center that would like to have a prototype of GaToroid to do proton flash research. And that, again, you can only do with a GaToroid if you want to do stereotaxis. But you're further away from clinical applications.
I see. Thank you.
Okay. So if there are no other questions, I would thank the speaker again. Thanks a lot, Luca. It was super nice. And nothing. I will close. Thank you.
Thank you very much.
Thank you, Lucas.
Thank you, Luca.
Bye-bye.